let me explain to you why we do a presentation like this. That's not strictly, these are the parts of PyLith. When you run quasi-static simulations, and I hope soon when you run some dynamic simulations, you have to solve a system of equations. And in order to do this, what we generally do and what we're doing in PyLith is to use a tool for doing it. And like all the tools that you use, you don't have to understand the inner workings of the tool, but you have to understand enough about it and have a surface representation in your mind to know when it's going wrong, to try and diagnose what part of it is going wrong and what steps you might take to fix it, right? So the analogy is something like your car. You do not understand internal combustion engines, or most of us in this room don't, but you know enough to know that the great screeching from the front may be your brakes and that you should put oil in it, you know, every 5,000 miles or something. So what I want to show you is if there is a great screeching from your solver, what might be going wrong and what you might be able to do to fix it. And so I'm going to try to explain at a high level, give you a model for understanding how solvers work, what they are doing, what happens when they go wrong. So just to say this again, this is the main point. We want to enable users to assess solver performance. That's the most important thing, rather than knowing what solvers are available and the names. You want to know how to check if they're performing well or performing poorly, and what to do in the case where they're performing too poorly for you. So I originally didn't have this mathematical background section, but I think I need it because we need to have some common terminology. So this will be interactive. I will ask questions. If no one answers them, I will pick someone to answer them. So what kind of thing, what do you care about when you run a simulation like this? What do you care about? What do you care about coming out of the solver? What's meaningful? What? Okay, accuracy, and just precisely what's accuracy? You care about stability. So stability is the thing you might care about. And stability, rigorously, is the sensitivity of the solution that you get out to the stuff that you put in. So we do care about stability. Stability is incredibly hard to assess. And so I don't even try in this presentation, but you might. Even simpler to assess, I would say you care about error. What's the difference from my computed solution to the true solution of my set of equations? Okay, that's the thing I think you would really care about. You wrote some equations, you ran a piece of software to solve them, you should be interested that it gets close to the true solution of the equations that you wrote down. That says nothing about how close the true solution of your equations is to reality, but this is all that PyLith can maybe promise you. Now, that is generally an uncomputable thing. We cannot get to the true solution. If we could, we would just give you the true solution. Okay? This is what we're going to call error. Error is something that we generally cannot tell you. In certain cases, we can. So if I, for instance, demand that a certain true solution hold, like an analytical solution or a manufactured solution, then I can report the error to you. But in most cases, I can only tell you this related quantity, the residual, which is how close is my computed answer to satisfying my equations. Okay, if I take my answer and I stick it in my equations, how close is that to 0? Now, I can measure that, and we do measure that, but it's a different thing than how close it is to the true solution. I'll try to show you how. So these are two metrics, but they're not the same. So this is the way that we tend to relate them. On the left, I have my computed solution U, and I have a true solution U star. And I want to relate that quantity to f of u. F of u is just, I have these equations f, I stick my solution in, how close is that to 0? And I don't want to talk in absolute terms, I want to say what are the relative differences, so I'm going to normalize them. I'm going to normalize the error by the norm of the true solution. I'm going to normalize the right-hand side by just the general scale of the problem. What do I get for f of 0? And it turns out in the linear case, you can relate these because the form of the equations is so simple. And just by some manipulation, you come up with this bound. where your kappa is a function only of the input matrix A. And this kappa is a thing that people call condition number. So the condition number is how much worse can the residual be than the error? Basically, how much bigger. So if I have a small residual, it doesn't necessarily mean small error, because you can get this blown up thing. And it has to do with the norm of the matrix, which just sort of sets the scale. You can control the norm of the matrix just by scaling. But it also has the norm of the inverse, and that has to do with how close you are to a singular system. And that's really the important thing for condition number. The norm of A just sets the scale of the problem. So that's why it's not a slam dunk when I'm solving a system of equations and I say, oh, you know, the system of equations are almost satisfied. Isn't this a great solution? Could be, but if you have a solution if you have a system of equations with really high condition number, then maybe not. Maybe you still have large error. So that's why we can't tell you definitively unless we know more about the equations that we're solving. Sometimes you can get theoretical bounds on how big the condition number is. So what I'm going to talk about today is how you might assess and then change the behavior of the solvers. And the way you change the behavior is to give options to the thing. So PETSc, you know, that handles all the solving, is controlled. Everything can be controlled by command line options of this form. Say solver type is gmres, which is a popular linear solver, or I can turn on the debugger. And what we tend to do to namespace things is to give these options prefixes. And this is the same thing that happens in PyLith, where you give prefixes. And all the PETSc options can be given to PyLith this way, either put in the PETSc section in the CFG file or just given as a prefix. You'll notice that the namespacing in PyLith is dots. The namespacing in PETSc is underscores. So they mix all right. I'm going to show examples with something in PETSc for nonlinear stuff and something in PyLith for linear stuff, just to show you both. So one thing that I didn't do last time that I thought was important this time is to just give you somewhat of a taxonomy of what are the characteristics of different solvers, just so you get a high-level idea. So if you could, you should solve everything you do with direct solvers. Direct solvers are incredibly robust. You are very sure that you have the right answer, and they're very predictable in terms of time. I can tell you exactly how long the direct solver will take. But they have downsides. The downsides are they take a lot of memory, and that's generally what prohibits you from solving your problems. Memory runs out way before patience in these situations, and especially if you don't have access to big machines. And then they are more expensive in terms of time, but not a lot more. So for 2D problems, you're only really giving up a log factor using a direct solver. So if you have a 2D problem, I would try as hard as you can to use a direct solver, because they can be very fast. Then if you want something that is more scalable, multi-grid, and you have an elliptic problem like we do here, an elliptic problem for the elastic part, then multi-grid is a good choice. It solves elliptic problems very fast. It uses very, very little memory, and the time is optimal in the sense that it takes order n time for n variables, although the constant is not optimal. When many solvers people talk about optimal, they ignore constants completely. They say they should have to say order optimal, and the constant can be very, very large. So beware solver people telling you about optimality. The problem with multigrid is that it's fragile. If it works, it is fantastic and never use anything else. If it isn't working, it is somewhat hard to figure out why and get it to work, which is why we don't use it all the time. There is an intermediate thing called domain decomposition. This is where you chop up a domain and you use direct solvers on the subdomains and then put it together somehow. And the somehow for putting it together, it determines exactly how robust and exactly how expensive it is. There are examples of this in PETSc. They're not general purpose yet. They're specialized. So we don't recommend them for general PyLith use, but we do use one of them as sort of a default solver, the additive Schwartz method, where you just solve in each block and hope for the best. Maybe you'd use some overlap. And then these three on top are standalone solvers. You can use them to solve problems. The fourth one sort of gets lumped in there, but that's a category error. If you're ever using a Krylov method to solve a problem, you are doing something wrong. Krylov methods are not for that. Krylov methods are to clean up mistakes in the upper three solvers. So the way they work is that they take existing solutions and they make them somewhat better. And they handle things that you've missed. It would be great if we never had to use Krylov solvers, but we do. So let me explain a little bit, because this tends to be what you're looking at when you're looking at PyLith output. A Krylov solver builds a small model of your problem in a tiny space and solves it exactly with a direct solver. That's what it does. And the question is, how good a model is that with a tiny number of vectors? Okay. So the strength of Krylov methods is that they're adaptive. They can select pretty efficiently the right features of your problem in this very small space when they solve it. So things that make multigrid break down, for instance, sometimes Krylov methods can correct. So a Krylov multigrid method is a lot more robust than multigrid alone. But they're not standalone solvers. They need to work in conjunction with another solver. Numerics people call this other solver a preconditioner, which is confusing and I never liked. It should be called solver composition. Preconditioning is a stupid term because it has no real definition. The only definition is preconditioners make it easier and faster to solve the problem, which is a dumb catch-all word. So the thing to remember about Krylov solvers is you should never be doing a lot of iterates on a Krylov solver, ever. If you find yourself doing hundreds of iterates, then something is horribly wrong, and thousands of iterates, you've completely lost your way. You should be doing 10, preferably, or 50. And as soon as you start doing a lot of iterates, scalability will suffer because you're doing a lot of inner products. And for parallel machines, inner products are just about the worst thing you can do right now, except maybe what you do with FFTs, which is all-to-all communication. So, as I said, preconditioner is a very vague term, but what it means is, suppose I used a second auxiliary solver in my problem, and suppose that that actually made it easier for me to solve. And that's what it means. It should be inexpensive, should accelerate convergence, but that's enough. So, when we are setting out to solve a problem, you should remember that taking someone's best effort, expert opinion for the solver settings is not what you should ever do. What you should do is solve it with a sledgehammer, okay? Take the slowest, most robust settings you have and solve it until you are absolutely certain that your physics is correct. Use coarser meshes, use simplifications, anything you have to do to check that it's right. And when it is completely right and you would like to solve a bigger problem, then and only then go away from the stuff that is guaranteed. Okay? So I would recommend always starting with LU. It's robust, it's completely performance predictive, you know how long it's going to take. We could actually print out how long it's going to take when you start solving if we wanted to. There's very little dependence on what kind of problem you have. The only way you can really break it is to feed it a singular problem or a problem that looks singular to it. And I'll show you that. It's also a great way to check that your problem is well specified. For instance, If you do the subduction zone problem and you put no restriction on the sliding of the slab, and it can just slide out, you will catch that because it will be a null mode, and if you factor the whole thing, it will show you that the problem is singular. And there's other things you can catch that way. So specification of boundary conditions, this is a good way. PETSc has built-in serial LU that works very well for most cases. In parallel, this is a difficult thing to write. Luckily, some French people and some people from Berkeley wrote parallel versions, which we can use. You just have to reconfigure PETSc and download those. What's in the tarball, Brad? Are either of those? Okay. Because of licensing issues? Yes.